All right, so welcome to another rigging basics. This is actually at first you're going to think this is not important. Like this whole thing related to right hand and left hand. I've never heard an animator have to talk about this. Thing is, left hand and right hand rules and what Y up and Z up is. You're going to probably hear that a lot from rendering engineers in particular. But this affects rigging, and as a result, it affects animation. And also, I don't know how many years I've seen like issues with Y ups and Z ups from one software to another. And for the most part, we have pretty decent pipelines to be able to transfer stuff between these softwares now. But there's been many animators who have had to deal with this in the past, and these are things that it's important to understand how it works. By the time you watch the whole video, you're going to be starting to think this is some Illuminati shit because it's all over the place. It's everywhere, even in your kitchen, even in your garage. I'm not kidding. Like by the time you're finished this video, you're going to realize just how important this whole left hand right hand rule is, and it's something that gets debated a lot by a number of people. So the first important thing is this image here that we have from someone named Freya Homer. Uh, the thing here is that the takeaway here is that some software uses the Y up and some softwares use the Z up. The easiest way to remember this is that if it's an Autodesk product, which is from AutoCAD, like originally, like Maya is not originally from Autodesk. It was purchased. But if you think that if you consider a AutoCAD system, which is for architectural things or pipes or vents or heating, anything that happens in a building that you need to draw, you use AutoCAD, and that's where they made the bulk of their money, and that's how they were able to come in and just buy everything. But the point I'm getting at is that all of that is a floor plan. Most of those are seen from above. So their x and y is generally from seen from up above, which means the z-axis is the one that goes up and down, and you're just looking at everything as if it was on the floor. In other softwares, like originally Maya and all these other softwares that are more like textbook math, in every textbook that you have where you're learning math, y is up on the page. So that's the front view for most of these programs. But you have a couple of exceptions where you have Unreal, which is using a floor plan kind of concept for a game engine is actually a very very smart move because you're designing levels much like you're doing architecture. So Unreal kind of said that's cool, and then decided to go left-handed. Go figure. They're the only ones that have that combo. But the important takeaway here is that every software has choices that have been made, and you just have to be consistent and know which software is doing what. Now, you're probably thinking there, well, what does this have to do? How does that affect me in any way? And it actually does. So let me just show you an example, okay? And we're gonna get first we're gonna understand what this right hand rule is, and I'm going to make it so that you're gonna see it directly in how we're doing and setting up our animation. So the first thing we need to do is bring out a right hand. So here's a right hand, and I suggest you do this with your hand as well, so you get used to it. And the first thing we're going to do is we're going to put our finger out, our index finger out, and we're going to say that is the x-axis. Okay, that direction is x. And then we're going to bring out our middle finger, and we're going to make sure that it's at roughly 90 degrees from the other one as much as possible. That's going to be our x and y. So in most softwares, we can all agree that you see this all the time. So in Maya, this would be front view. In other softwares, like we've mentioned already, this is the floor plan. The x and y goes in that way. Okay, but for right now, for us as riggers and animators, what we're really interested in is the z-axis. Okay, so we're setting things up so that our thumb, is going to give us information about where z goes. So that means that if I use my right hand, z points in this direction. So relative to these two axes, this is where the z points. So if you were to use your left hand, what you're going to realize is that it's going to point in the opposite direction. So that's the difference between left-handed and right-handed. If you're using a right-handed system, the positive direction for the third axis is going to be aligned this way. If it's a left hand, it's going to be pointing in the other direction. All right, so real quick here, X and Y. Imagine they're what we call vectors. Vectors is just a fancy term to say what direction it points. So imagine the point where all of these three axes touch is your origin. Like let's say that's 0, 0, 0. In the case of X, imagine where the tip of the X is. That coordinate would be its the vector, the just its position relative to where it all meets. That would be its vector. That would be what we would refer to as a vector. And the same thing for Y, where the tip is, and the direction that its position relative to that would be its vector. So in the case of the X, it would be 1, 0, 0. In the case of Y, it'd be 0, 1, 0. In the case of Z, that would be 0, 0, 1. All right. And here's something that we're not going to go into too much, but I'm just going to mention it. There is something called a cross product. A cross product takes two vectors, and when you do a cross product of those two vectors, it will always give you a third vector that is 90 degrees to both the first and second vector. So that means that if I were to do a cross product between this direction and the Y direction, it would give me the Z axis in a right hand rule. All right, that's the other thing. Depending which software you're in, and you do the cross vector math, it will give you this. And this is actually a very handy thing. In it's not just like math. It's and it's useless to us as animators. No. We can actually use cross vectors to do all kinds of neat things. Like I can make a look at constraint because I know how to use how to use a cross vector. Because if you think about it, you have the direction that you want to be looking at, and then you have like have you ever noticed that in the description of a look at there's the concept of an up vector? Well, guess what? That's just a cross vector there, where you're just defining which direction's up and where your target is, and it will calculate basically a transform, which then aligns everything so that it looks at it. And it's everywhere. All of your constraints are based in some way to the. I've rewritten just about every constraint, and I can tell you that the cross vector is something that's very handy. Okay, that's a little bit too much information. Just know that it exists, and it can also be used for torque. Not really that useful for now. That's not really useful for animation, but at least cross vectors are. Okay, so moving on. Now, the next thing that we need to do is start to visualize this axis, okay? So if you still have your hand out and you're doing this, I want you to start visualizing that motion going from X to Y. So just to reiterate, we're going in this direction. Another way of placing your hand to do this would be to kind of visualize it this way. So I'm gonna bring this out now. And basically, that motion of the X to Y fingers, instead of doing that pointing thing, I'm going to do a curling of fingers like this. And we're going to just visualize it a little bit differently just for a moment, because this is actually quite handy to us because of the circle is very much like the gizmo ball from rotation, when we're in rotation. And the Z-axis direction is still the thumb. So this is a very clean way of visualizing how we align our Z-axis, because that's important to us. Remember from all the other videos, we defined that this is really important. So here's another way of visualizing it. So if you rotate like so, if you rotate your hand like that, it is going positive. Okay. If you rotate the other way, it's a negative. Here's where we're starting to get into the Illuminati stuff. You don't realize it, but every jar that's in your house is aligned this way. It's meant so that you turn the lid in a certain direction, and every jar has to follow this convention because, again, consistency is key. So if your jar, you want to close the jar, you do a positive Z, and that will push the jar lid in the right direction to lock it. When you spin in the opposite direction, the negative direction, you're actually loosening the jar lid and it's opening. So already we can see that there's some stuff that's starting to creep into our day-to-day routine. So the best one, though, the one that I find that is the most like the one that you should take away from this video, is if we use a screwdriver. Now the screwdriver is fantastic for visualization because you just have to put your thumb in the direction of the screwdriver, and there's a motion, righty tighty, lefty loosey, right? So this concept is really handy for us because if you need to understand where, like, I made this screwdriver blue on purpose. So if you want to imagine how you would turn your knee, or where the z axis should point when you bend your knee, imagine someone shoving a screwdriver on the side of the knee and turning. That is the direction, and that is the axis that the z-axis would point. That is the direction that the z-axis would point, and that's the motion that it would do. So that is a much easier way to visualize. Now, so far we've gone all this way just to get to visualize a screwdriver, but there's more. So here's another one. Bet you never thought of this one. So this is just a normal triangle, and the order in which the vertices are calculated or are presented is actually extraordinarily important. So 1, 2, 3 is the order of vertices on a triangle. All right. So this is just an example. The order in which the vertices are set will determine in which direction the normal points. Go figure. You see this? This is nothing more than I copied this and just turned the Z into an N. And that now describes the direction in which you're going from 1 to 2 to 3. And in that circular fashion, you are now controlling the normal. So here's the fun part. If I were to scale this negatively on the other side, you're basically flipping the normal by doing that. Now you understand why negative scaling, can affect normals. Because when you freeze the object, it pops the normals, usually. Right? Because there's an internal thing that most Autodesk products have that when you do a negative scaling, it kind of goes, I have a negative scaling, so flip all the normals before the user, code 16 type of thing. And then, but when you freeze it, that because there's no more negative scaling, there's nothing there to stop it from flipping the normals, and that's why it flips the normals. So the most important thing here is that to note that the order of vertices on a triangle can determine where the normals are. And another fun fact is, if you've ever wondered what the tangent space is on a triangle and how it works with how it works in conjunction with UVs, well, you're looking at it. The like, basically imagine the line or the edge from 1 to 2 and 2 to 3 in the UVs. Well, that's your tangent space. And it has to do with which order you put them in for your triangle here. So that's something to consider. That basically the right hand rule is basically everywhere in 3D, and you need to remember that it has to be consistent. And for us, for rigging, we just need to remember these things to be able to manipulate later the animation in a coherent way. That we can, and for us, the z-axis being an incredibly important axis, we will keep this in mind. So hopefully you found this video not too confusing. I know it's kind of a weird one because we're talking about jars and screwdrivers, but frankly, this is we need to start visualizing these things because they're of utmost importance to us.